Dear student, here I am going to continue the next part of strength of organic acids and bases. So in previous video, we discussed about the aliphatic bases. Now, in this video, I am talking about the aromatic bases. Because generally, aromatic bases are weak bases as compared to aliphatic bases. In aliphatic bases, there is a presence of electron donating inductive effect which increases basicity. While in aromatic bases, due to aromatic ring, as it shows electron withdrawing resonance effect, so it decreases the basicity. Remember, this is not always true. It depends on, again, if the other effects are present. So no doubt, in case of aliphatic bases, though there is a presence of electron donating inductive effect shown by the alkyl group, but if that alkyl group is attached to electron withdrawing group, then you can see there is a different scenario we can see. So this is not always true that aliphatic bases are always strong base as compared to the aromatic bases. But mostly if you consider without having any donating group or withdrawing group, just on the basis of simple aliphatic base and simple aromatic base, without any group present on that ring, then always the aromatic bases are weak bases as compared to aliphatic bases. We discuss one example for this. So this is a aliphatic base where on this cyclohexyl group, there is no any other group which shows the other effect. So only cyclohexyl group is there. And in case of aniline, only pH group is there. Again, there is no any other group which is present on the aromatic carbon. So I call this is a aliphatic base and this one is aromatic base. In case of an aliphatic base, cyclohexyl ring shows a electron donating inductive effect, that is plus I effect. So it donates its electron density to this heteroatom, that is nitrogen atom. Because of that, the electron pair which are present on nitrogen are readily available for donation to a proton. So as it readily donates its electron density, therefore it has to be a strong base. So you can see pK is 10.68. But in case of aniline, what happens? Whatever the electron density is present on this nitrogen atom, it get delocalized in aromatic ring. So we call this as a electron withdrawing resonance effect shown by this phenyl ring. Due to that, electron density which is available on this nitrogen atom not readily available for donation to a proton. Because of that, this nitrogen atom donate its electron density less readily. Hence, this has to be a weak base. And you can see here 10.68 and this pK value is 4.62. As pK go on decreasing, so basicity also decreases from A to C. But in case of ammonia, you can see there is no plus I effect as well as there is no minus R effect. So plus I effect always increases the basicity while minus R effect decreases the basicity. So ammonia lies in between these two examples. There is no plus I effect and no minus R effect. Hence, it is less basic as compared to A, but it is more basic as compared to C. So, the electron donating inductive effect, remember always, it increases the basicity because the electron density which is available on the nitrogen atom that can be readily donated to a proton, so it acts as a strong base. So this is a simple example where we can show a aliphatic base is always a strong base as compared to aromatic base only when it is true if there is no substituent present on the ring. So no substituent on the ring. Now look at how the electron pair which are present on the nitrogen atom, how they involved in delocalization. So nitrogen electron pair, it transport towards the orthocarbon, so orthocarbon negative charge, then it gets shifted towards the para-carbon, so there is a para-carbon, there is a negative charge. Again, due to this delocalization, again orthocarbon having a negative charge. So look at the nitrogen atom, as it donates its electron density to aromatic carbon, therefore no electron density available with this nitrogen, that's why there is a plus sign. This plus sign indicates electron pair is not with this nitrogen, now it is with the aromatic carbon. Due to that, when nitrogen atom has to donate its electron density to a proton, then this donation is not readily possible. Because of that, the donation of electron density to a proton is little bit a slow process and hence it is a weak base. So when it donates its electron density to proton, it converts to NH3 plus. Why the plus sign is here? That plus sign is on nitrogen atom. Once the electron pair present on nitrogen atom are used up, then positive charge on nitrogen that you have to write down, and this is a anhelium cation. So in that way, the phenyl ring shows electron withdrawing resonance effect. Now this is the new example. Ammonia, phenylamine, that is aniline, diphenylamine and triphenylamine. So you can see every time one phenyl group we are going to add from A to D. And look at the pK value, pK goes on decreasing. So pK goes on decreasing from A to D. As pK decreases, basicity also decreases. So what you see the difference in all the structure, every time you are going to add the phenyl group. And what is the role of phenyl group? Role of phenyl group is the electron withdrawing electron withdrawing resonance effect. So how we can conclude it? From A to D, each effect go on increasing, electron withdrawing resonance effect go on increasing from A to D. As the electron withdrawing effect go on increasing, electron withdrawing resonance effect go on increasing, the availability of electron density on nitrogen atom decreases from A to D. Hence, electron donating capacity decreases from A to D. So, in compound D, due to presence of 3-phenyl group, the compound is no more basic. This is the first factor, that is introduction of electron donating groups. Now, in this example, we are talking about this electron donating group we are going to introduce on the nitrogen atom. So, aniline, no electron donating group. In N-methylaniline, one methyl group is attached to the nitrogen atom, and in N-dimethylaniline, two methyl groups are attached to the nitrogen atom. So remember, in all the example, the minus R effect is present, that is shown by the phenyl ring. So minus R effect is same in all the structure. But which effect go on increasing? In aniline, the plus I effect shown by the methyl group is absent. So compound B, only one plus I effect, while in compound C, the two methyl groups are there. Therefore, electron donating inductive effect is more in case of C as compared to B as compared to A. So what is the role of electron donating inductive effect? The methyl group donates its electron density towards the nitrogen atom, and hence as the plus I effect go on increasing from A to C, it increases the availability of electron density on nitrogen atom. So more the electron density, more is the capacity of donation of electron density to a proton. So basicity increases from A to C. So now this group we added on the nitrogen atom. Now in the next example, the methyl group that is added on the aromatic carbon atom. So aniline orthomethylaniline, metamethylaniline, and paramethylaniline. So electron donating group is added either on nitrogen atom or on ring carbon. Then there is small increase in pK value. You can see 4.62, 4.67, 5.10, a little bit increase in the pK value, or we can say the plus I effect increases, therefore the basicity also increases. So that we cannot see in case of orthomethylaniline, there is a little bit decrease in the basicity. So overall, we conclude that introduction of methyl group on the nitrogen atom of aniline or on the ring results in small increase in pK value. Now here we added a group which having a unshared pair of electrons. Now this hydroxy group, there are two unshared pair of electrons are there. Now because of this unshared pair of electron, this hydroxy electron pair get involved in resonance. So due to this, now this aromatic ring, instead of electron withdrawing effect, its effect is now changed. It shows electron donating effect. So look at here, whenever a hydroxy group is present at para position, the electron pair of oxygen get shifted to that carbon atom which is attached to the NH2 group. So you can see the negative charge is on that carbon atom which is attached to the nitrogen atom. As this carbon is electron rich, as this carbon having the excess of electron density, and that electron density is obtained from which group? That is obtained from hydroxy group. Because of this, now this carbon not showing a minus R effect. Instead of that, it shows electron donating inductive effect. So because of the electron donating inductive effect, it increases the electron density on this nitrogen atom. As the electron density on the nitrogen atom increases, so it readily donates its electron density to a proton, so it acts as a strong base. As compared to aniline, you can see para-hydroxyaniline pK value is 5.30. So in aniline, the phenyl ring shows which effect? It shows minus R effect. But in case of para-hydroxyaniline, no doubt phenyl ring is there, but now its role changed to plus I. So here there is a presence of which effect? There is a presence of a minus R effect. So phenyl ring shows a minus R effect. But as soon as you introduce the hydroxy group, the ring is now no more electron withdrawing resonance effect, but instead of that, the ring shows electron donating inductive effect. The reason behind it, because of this type of a resonance, the carbon which is attached to the nitrogen atom is electron rich, and hence it shows a plus I effect. So due to that, here you can see there is a presence of a plus I effect. So it increases the electron density on the nitrogen atom. Once the more the electron density on the nitrogen atom, more is the capacity of donation of electron density. So this type of resonance is possible in case of para-hydroxy group as well as in case of a ortho-hydroxy group. But such type of donating effect we cannot see in case of such type of resonance effect we cannot see in case of a hydroxy group which is attached at the meta position. So when the hydroxy group is attached to the meta position, then it increases the electron density on para carbon with respect to hydroxy group. So hydroxy group is here. With respect to that, this is a para carbon. So it increases the electron density on this para carbon, and then para carbon carry a negative charge. This para carbon is not attached to the NH2 group. So because of that, as compared to ortho and para, that this is less basic. But in case of ortho, that due to the resonance effect, the para increases the electron density on the nitrogen atom. So it increases the electron density on that carbon atom which is attached to NH2 group. So in both the cases, in case of orthohydroxy and parahydroxy group, the hydroxy group increases the electron density like this. We can see here this resonance effect. It increases the electron density on this carbon atom which is attached to the NH2 group. So that is true with respect to orthohydroxy and parahydroxy, but it is not possible in case of a metahydroxy group because it increases the electron density on this carbon which is para with respect to this hydroxy group. So you have a negative charge on this carbon, not on this carbon. Because of that, no doubt it shows the electron donating inductive effect, but that is a less because the distance is more. Instead of here, now it is here. As the distance increases, the inductive effect decreases. So which effect? Electron donating inductive effect. So in metahydroxyaniline, there is a less electron donating inductive effect as compared to ortho and para. So as you increase the plus I effect, automatically the availability of electron density on nitrogen atom increases. Hence, that increase the capacity of donation of electron density. Hence, this act as a strong base. So pK goes on increasing from A to D. So basicity increases from A to D. So you correct this one. That is basicity. So you correct this as basicity increases from A to D. In compound A, there is no hydroxy group, so electron donating inductive effect is absent. Electron donating inductive effect increases electron density on nitrogen atom. So in compound B, C, D, availability of electron density is more as compared to compound A. So compound A is weak base among all. When an electron donating group is present at ortho and para position, then it shows a prominent effect. So ortho and para positions, you can see that these two compounds are more basic as compared to meta. In compound C and D, hydroxy group shows electron donating resonance effect. So it increases electron density on that carbon atom which is attached to NH2 group. Again, the resonance effect shown by parahydroxy group is more effective as compared to orthohydroxyl group. The reason behind this that we already discussed, paraquinite structure is more stable as compared to orthoquinite structure. So paraquinite structure is more symmetric structure as compared to orthoquinite structure. Therefore, the resonance effect shown by the para group is more preferred as compared to the ortho group. So due to this, para structure shows more resonating effect. Hence, para is a strong base. Hence, in compound D, the carbon which is attached to NH2 group is more electron rich as compared to compound C. So, compound D is more basic than compound C. But what happened in compound B? In compound B, the electron donating resonance effect shown by hydroxyl group increases the electron density at that carbon atom which is not attached to the NH2 group. So compound B is weak basic as compared to C, D, but strong as compared to A. So now in this example, instead of hydroxy group, now there is a presence of methoxy group. You can see the same sequence. In case of aniline, there is absence of methoxy. Now this is metamethoxyaniline, this is orthomethoxyaniline and paramethoxyaniline. They every time again oxygen having unshared pair of electron that involved in resonance. So resonance effect we can see here due to that resonance effect, and again this resonance effect is electron donating resonance effect. Because of that, the electron withdrawing capacity of this vinyl ring decreases, rather than that it becomes an electron donor. Again, this effect is prominent when the methoxy group is present at ortho and para position as compared to meta position. We can see the pK value go on increasing from A to D. So automatically basicity also increases from A to D. So this is the resonating structure where methoxy group transfer its electron density to that carbon atom which is attached to the nitrogen atom. So now here we can see which effect. So this shows electron donating inductive effect. So methoxy group shows electron donating inductive effect. And this structure we call it is a paraquinoid structure. So it is more symmetric structure, therefore it is more stable structure. So same you can write here, the same explanation. Again you correct this statement, that is this word you corrected, basicity. The pK goes on increasing from A to D. So basicity also increases from A to D. In compound A, there is no methoxy group, so electron donating inductive effect is absent. Electron donating inductive effect increases electron density on nitrogen atom. So in compound BCD, availability of electron density is more as compared to compound A. So compound A is weak base among all. When an electron donating group is present at ortho and para position, then it shows a prominent effect. In compound C and D, methoxy group shows electron donating resonance effect, so it increases electron density on that carbon atom which is attached to NH2 group. Again, the resonance effect shown by paramethoxy group is more effective as compared to orthomethoxy group because paraquinoid structure is more stable as compared to orthoquinoid structure. Hence, in compound D, the carbon which is attached to NH2 group is more electron rich as compared to compound C. So, compound D is more basic than compound C. While in compound B, electron donating resonance effect shown by methoxy group increases electron density at that carbon atom which is not attached to NH2 group. So, compound B is weak basic as compared to C and D, but strong as compared to A. Now, this is the next example. The electron donating group present at nitrogen atom as well as electron donating group present on the ring carbon. So this is N dimethyl aniline. This is 2,6-dimethyl. This is number 1 carbon. 2, 3, 4, 6. That is 2,6-dimethyl. N dimethyl aniline. Nn, that is 2 methyl groups are attached to nitrogen. So N dimethyl aniline. So what you see here, that these two methyl groups causing a non-bonded steric interaction. So we call it as there is a steric hindrance. Now in case of this, both this methyl group donate its electron density to this nitrogen atom, but this nitrogen electron pair get involved in resonance. So this aromatic ring shows a minus R effect. So there is a presence of minus R effect. That electron density get transferred in the aromatic ring. Due to that, now you can see here, there is a positive charge on this nitrogen, indicate that now nitrogen, there is no electron density for donation, so it acts as a weak base. What happened in this case now? In case of the second compound, due to this steric problem, to avoid this steric interaction, the ring change its orientation because of the nitrogen atom and the ring, they not remain in one plane. To minimize the steric interaction, the aromatic ring change its plane a little bit. Due to that, electron pair of nitrogen atom and the aromatic ring, they are not in plane. If they are not in plane, then automatically the electron pair of the nitrogen atom not involved in resonance. So if the electron pair not involved in resonance, that means the electron pair readily available. If the electron pair readily available for donation, so indicate what? Its donating capacity increases. If its donating capacity increases, so that indicate 2,6-dimethyl and then dimethyl aniline is strong base as compared to N dimethyl aniline. So in n-dimethyl aniline, there is electron withdrawing resonance effect, but in this case, the electron withdrawing resonance effect is absent. The reason behind it, the steric hindrance changes the planarity of the ring, so nitrogen electron pair not involved in resonance. So same is written over here. And then dimethyl aniline, electron pair of nitrogen atom delocalized in the ring. So electrons not available for the donation to a proton. Therefore, it is less basic. In 2,6-dimethyl and then dimethyl aniline, the two methyl group at the ortho positions to NME group sterically interact with the methyl groups of the nitrogen atom. Due to this, p orbital of the nitrogen atom goes out of the plane of the benzene ring, thereby inhibiting the resonance. So steric effect inhibited the resonance. Hence, electron pair readily available for donation to a proton. Therefore, it is more basic. So for this, you go through the reference book